Fossils only tell half the story.
Fossils only tell half the story.
We have long relied on inference for soft tissues.
We have long relied on inference for soft tissues.
But now, artificial intelligence is changing that paradigm. This is the frontier predicting life from remaining structure. And now that we understand X, let's explore Y. The challenge begins with 3D bone scans. These scans provide crucial measurements of attachment points. But muscle mass and organ placement remain hidden variables. Historically, reconstructions were informed by artistic guesswork. Our protagonist, a lead researcher, seeks objective truth. But the key lies in training the AI on modern analogs. Vast libraries of extant animal anatomy feed the algorithm. These systems use deep learning to find hidden patterns. But the AI analyzes microscopic evidence of muscle scarring. It correlates these scars to known muscle force vectors. This process refines the initial predictions iteratively and precisely. Organ placement, too, benefits from volume constraints. The system assigns confidence scores to every calculated feature. This moves paleontology toward evidence-based visualization. We can now simulate how different muscle fibers function. But contrast this with older models reliant on simple scaling. The researcher watches the transformation with cautious optimism. But next, we integrate these forms into simulated ancient environments. Movement dynamics become testable scientific hypotheses. And does the reconstructed leg structure support the inferred speed? But even skin texture and coloration use probabilistic modeling now. This methodology applies across vastly different life forms. The reconstruction even estimates visual acuity based on orbit shape. The input data must be exceptionally clean for good output. But noise reduction algorithms scrub contamination from the scans. Every parameter is a choice weighted by millions of comparisons. Where wrapping the form requires precise surface tension calculations. The human expert still guides the overall scientific narrative. The AI provides options, the paleontologist makes the final call. We are seeing the most complete representation yet possible. Metabolic rates are inferred from predicted organ volume data. But heat regulation informs decisions on insulation, like fat or feathers. The structural integrity must match the expected forces of movement. When data contradicts itself, the AI flags the uncertainty. This forces deeper investigation into the ambiguous fossil evidence. Better fossils lead to better AI predictions later on. A next-generation scanning technology captures unprecedented detail. But the AI digests this high-fidelity input immediately. The comparative anatomy is now executed at digital scale. A muscle attachment points dictate feeding mechanics precisely. Uneven vocalizations can be modeled based on predicted larynx structure. But this allows for holistic ecosystem reconstruction, not just singular beasts. We virtually step into worlds previously only imagined. But the role of the scientist evolves into architect of possibility. These details bring an emotional resonance to the science. We move past sketches to tangible, data-driven understanding. But the gap between bone and biography is rapidly closing. Or imagine the sheer density of the reconstructed flesh and sinew. When this AI is reconstructing not just shape, but existence itself. The underlying code is a testament to collaborative human ingenuity. This partnership opens avenues for understanding extinct pathology too. But every simulation challenges the next generation of discovery. And the results feed back, creating a constantly improving knowledge loop. We are witnessing the past being digitally resurrected, layer by layer. The future of paleontology is no longer just about bonuses, it is about life.